Hi, Sam here from Roberts Geospatial. Just for fun today, we're going to look at some bathymetry data. This is from the Gulf of Mexico. The website's in front of you now. It's from the Bureau of Ocean Energy Management, and you'll find their Gulf of Mexico Deepwater Bathymetry Grid. So this grid has been created, you can see it here, it's been created by stitching together a whole bunch of 3D seismic survey data acquired from the oil and gas exploration and drilling industry out there. So down here you'll find the TIFF files. Of course, I've downloaded those TIFF files and merged them into an MRR for the purposes of this demonstration. So just quickly, here's a picture I found on the internet. This shows the Gulf of Mexico, and all these little red dots up here are oil wells. I guess there are thousands of them. So the Gulf of Mexico produces about, I think, 1/3 of the United States oil and gas. Typically, in the past, the oil has been taken from shallow water. But as you go out into the Gulf, it gets deeper, and so these oil wells out here are from what you call deep water. And then as time goes on and they exhaust those resources, they're going out into what's called ultra deep water. And you can see out here, just they've picked out a couple of particular wells. So here's the Tiber well, the world's deepest offshore well. This thing goes down 35,000 feet from sea level. Perdido here is operating in 8,000 feet of water. And of course the Deepwater Horizon well, which we've all heard of because of the movie, is just out here, or was just out here, off of the Mississippi River Delta. So I'll just go to ProRaster. ProRaster Premium I'm using today. You can find that on the Windows Store. So I've got a visualization here of the Earth. So we're combining Merit DEM data for land, JEPCO 2020 data for bathymetry, and in here we've got the bathymetry dataset from the BOEM. So here's the Gulf of Mexico. Let's just take a look around. Firstly, down here on the Yucatan Peninsula, if you look carefully, you can see these circular features. And they are supposedly left over from the Chicxulub meteorite impact. So the meteor hit about here, and if you draw a big circle in here, that's the extent of the Chicxulub meteorite impact, which is, of course, the one that's implicated in the destruction of the dinosaurs. So around here, Mexico have their oil drilling, oil extraction operations, and then as you go north up to the United States, you can see here this is the channel levee that's being produced by the Mississippi River. Mississippi Delta is here, and then we have all the oil and gas drilling operations here in the Gulf of Mexico. Over here you can see a very significant feature. This is Florida Escarpment. This thing is an extraordinary about 2 kilometer high cliff in water that is, let's just have a look here, 3,300 odd meters deep, and over here in the Gulf of Mexico the deepest part gets to around 3,800 meters deep. Here where all the oil exploration is going on, it's down into water around 2,000 meters deep, so they're going down to around 2 kilometers deep. Although there's the Perdido well that I mentioned was in slightly deeper water over here. So the amazing thing about this data set is this extraordinary, let me just turn those tooltips off again, it's the extraordinary nature of this seafloor. And this is caused by salt and hydrocarbons. So largely I suppose it's a result of the salt. So the salt gets squeezed around by pressure like toothpaste, and of course it causes diapers and so forth, and that deforms the sediments, creates hydrocarbon traps, and that's what they're chasing in this area. And you can see, perhaps over in this area, quite typical sort of terrain where you've got these mounds which are caused by salt underneath. And over the other side here, similar kind of terrain. In the center, it seems to be, it's not so much mounds. There are mounds here along the edge of the escarpment, but up here it seems to be mainly depressions. So let's take a look at this in 3D. So I've got the data set here in 3D. So if we come over, and it's got some vertical exaggeration. So over here we're seeing these salt diapers coming up as positive mounds on the seafloor. And again over this side in the, whoops, come on, keep control, over here in the eastern side, and then you can see this extraordinary Florida Escarpment. But then over here in the center, if we just sort of take a look at it like this, you can see that mostly it's not coming, the expression is not above the seafloor, it's below the seafloor, and you can see all these deep depressions and so forth in this central area. So, really extraordinary terrain. And over this side, you've got, I think there's a canyon in here, the Perdidos Canyon, and then the Alaminos Canyon. There's another one in here. I'm not sure what the name of that is. Oh, I've lost control. This software, in case you're wondering, is called PA. I helped write it about 20 years ago, but you can still buy it from Datamine. They have a 64-bit version now. This is the Mississippi Canyon over this side. So let's come back to our Earth Atlas display, and we'll just look at some individual features. So with this visualization with the kind of blue color scale, we get an idea of what's going on, but we can't really see what's a positive and what's a negative feature. So I wanted to do some high pass filtering of this raster set, which is a bit problematic because it's a large raster. It's something like 100,000 by 40,000 cells or something like that. And just briefly, the way that I went about this to get a high pass filter really, really quickly and easily was to take the MRR raster, which has a full power of 2 data pyramid. You suck out one of those levels in the data pyramid, and then you use a virtual raster to subtract that from the original raster using high quality, very high quality cubic spline interpolation, and that leaves you with a high pass filter. So let's take a look at say 4096. So now I'm coloring this thing just locally, and you can see the features. So you've got these mounds over here, all these depressions in here, and this I think this thing here is called the Sigsbee Salt Canopy, and it's kind of a positive feature before it dives down into the abyss. So let's just come over here. Over here, perhaps they've picked out a few examples on the website, so I'm just going to basically follow that. Firstly, they say, well, look at all these sand dunes in the sediments around here. And let's go to something a little bit, go to 1024. So now we're going to a higher frequency, and so you can see these sand dunes quite clearly. And then you have these mounds, and in these mounds you've got all these pockmarks, possibly or supposedly caused by methane hydrate emissions. So they've just gone pop and popped out a whole bunch of methane hydrate or methane. And you can see those features all over. In addition to that, there are other things like what look like, for example, little mud volcanoes. So something like this, for example, like a little mud volcano. You see these tiny little features and lots of little depressions. They pick out over this side. We come right over here. I think it's over here. One in particular. No, it's not it. It's this one that they picked out. Here's a mound caused by upwelling salt. And in here you can see it's kind of faulted and the sediments have fallen away. And then there's been these explosions or emissions of methane or perhaps hydrocarbon and created these little pock marks in the terrain. So so if we come over here, come past these two canyons and this particular one in here, over here on this side of the data set, I think in here, yeah, you can see these extraordinary features which are described as furrows, and they're enormous and very, very long, and apparently water is flowing down these things and along them. They're not ripples, they're furrows, and they're all over the place if you go looking for them. So quite amazing. So let's come over to, we'll come past the Mississippi Canyon, and let's take a look at this amazing feature. This is the Florida Escarpment. I've got this in 3D, so let's come back to PA, go to that second window. So here the thing is, this is the Florida Escarpment in 3D, and there's no vertical exaggeration on this. So this thing is virtually vertical. Whoopsie, let me come back a bit. Whoa, this thing's hard to drive. It's virtual. Oh, come on, man. Yeah, now I've got a bit of control of it. This thing's almost vertical, and approximately 2 kilometers high. And if this was at the surface, you know, we wouldn't be going to America for holidays to see the Grand Canyon. We'd be going to go and have a look at the Florida Escarpment. It really is an amazing feature, and it's sitting 3 kilometers below the seafloor. Down here we're looking at a depth of about 3,000 meters. So that's an extraordinary feature. Let's go back to Earth Atlas and come over here, and there's another thing which really amazes me, and you can just see it here. It's called the Lloyd Ridge, and it's a levee channel. So if I zoom in down here, you can see that this thing is a channel. There's been a current flowing down here, and it's created this. This is actually a mound that's been created over time, and it's worn away this channel. So there's some papers floating around on the internet that you can go looking for about this Lloyd Ridge levee channel, and some of them have pictures of the actual 3D seismic. So this thing isn't just an expression on the surface. If you look at the 3D seismic, you can see it continuing at depth, and you can see the history of the sedimentation of this thing. And so if you come up here, I mean, it's about 500 odd kilometers long, and as you go further up, it starts to get destroyed by turbidites and so forth. But down here, it's really interesting. You can see that here it's a negative channel, but as you go further up, it appears to become a positive. It's actually a positive mound, and here it's a highly visible mound. So if I'm just going to go to one of my high pass rasters. We can see this in a little bit more clearly. So here's this thing. Here's the low resolution data where you see absolutely nothing, and here's the high resolution data which has all this detail in it. So So it sort of gives a bit of a demonstration of what we're missing out on by not having high-resolution bathymetric data. You know, what else is out there? It's just amazing. Here you can see a kind of an oxbow loop that's been cut off. And anyway, as we follow this channel up to the northwest, you can see that it starts to become, firstly, it flows off this way at one point, and then up in here it starts to become a positive feature, and here it's actually a mound. And I'd like to know how this thing forms. I mean, I'm not a sedimentary geologist, but if you're going to have a flow of a river effectively flowing on the bottom 3 kilometers deep on the bottom of a salty ocean, then that water's got to have a pretty high density. Now it's fresh water, and apparently the source of it was a river called the Pearl River, and I can only assume that it was absolutely chock full of sediment in suspension to give it a higher density, so that the water actually, you know, flowed as a continuous mass, and for a long, long time. I mean, obviously, for many, many, many thousands or maybe millions of years, I don't know, but for obviously a long time to create this feature. If anybody knows how these things form and can give some insight into that, I'd be interested to hear about it in the comments. Anyway, so let me just move on. So we've looked at the escarpment, we looked at the Lloyd Ridge. So just coming back to the Earth Atlas, so let's just have a look at one other thing. I was just going to show you the effect of sea level change around here. So in this visualization, green is the current coastline, so greens and browns for above sea level. And then this light blue is the continental shelf, and it just starts to go into this kind of aqua color on the edge of the continental shelf, and then into the darker blues as you go deep. So you can see that a lot of this area around here is quite shallow. Now, to simulate sea level change in a program like ProRaster, I guess you can either change the data itself, or you can change the color scale, and actually it's easier to change the data itself. So if I go into this thing, and I'll go into the data conditioning, and in data conditioning you can set a transform. So I'm going to put a 120 meter transformation, and then so that's going to lower the sea level by 120 meters, and then I'll choose that for the color in all of these rasters. So I'm just applying this data conditioning. So this happens on the fly. So now you can see that the shoreline has moved way out here. Florida is now hell big. All this shallow coastline around the Gulf has been turned into land. And these enormous land masses out here have appeared. And over here is the Bathymetry Road, in case you've been watching that Netflix documentary and you're wondering where Atlantis is. Well, that's where it is. Well, maybe. And but you can also see that with that lower sea level, the Gulf is fairly cut off from deep water. You know, it's quite isolated from the Atlantic. So I imagine it would have been fairly salty at times with lower sea level. And I was just going to look in here because if there is Atlantis, then you wonder whether this interesting pattern might indicate something. So let's go into the terrain, look at the shadow here, bump up the shadow, make it say 75% or something. And actually that's not the terrain, sorry, we need to look at the bathymetry, and we'll bump that up. It's green because it's terrain, but actually it's bathymetry data. So are these strange patterns an indication of roads that lead to Atlantis off the coast of Florida? You be the judge. Anyway, that's a nice visualization of sea level during the Ice Age in this particular area in the Gulf. So look, amazing data set, really worth taking a look at. easy to download. There are problems with those TIFF files. There are always problems with TIFF files. In this case, the null value has been incorrectly specified. Anyway, you have to work your way through that problem, and if you do, you'll find a fascinating data set to look at. So thanks for watching.